let's find the area of the surface of revolution. We actually don't need the picture to solve it, but let's go ahead and draw it anyway, just so we can get a visual for what's going on. So we got this parabola, y equals the square root of x, and it's being rotated around the x-axis. And the formula that we have works only when we're rotating around the x-axis, so that's convenient. The picture is we'd rotate it around and get this funnel shape, this what's called an elliptical paraboloid, and we would find the area of the front and back of this elliptical paraboloid would be given by the integral from t equals a to t equals b of, we can pull out the 2 pi to the outside, 2 pi y of t ds. And that ds, that arc length differential, expands out to dx dt squared plus dy dt squared dt. Now, in order to even use this, though, we need parametric equations, and we don't have them for this parabola, the parabola y equals root x, so we need to make them up. Now, when you have a curve described by a function, y equals a function of x, the simplest way is just let your x equal to t, and then your y would equal the square root of x, and that's just t. Okay, I don't really like this parameterization though. If I used it, then since our x is going from 0 to 4, then that would give us t is between 0 and 4. But the problem again is that I need to use the derivatives, and while that gives me a nice x derivative, dx dt is 1, my y derivative, dy dt, that would be 1/2 t to the negative 2, or sorry, t to the negative 1/2, so that would be the square root of t in the bottom. I don't want to have to deal with that. That looks kind of messy to handle up here. Okay, so let's back up just a little bit. Let's find a better parameterization. And since I want my derivatives to be nice, maybe instead of letting x equal t, I'll start with y is equal to t. And if I do that, then I get that the square root of x is t. So I replace the y with a t, and that tells me that x is t squared. And that seems like a much nicer pair of parametric equations. All right. Of course, since y is equal to t, I'm going to use the y values 0 to 2. So t ranges from 0 to 2. Okay, and I think that'll be a little bit nicer for us. All right, my y is t, my x is t squared. That tells me that dx dt is 2t. And then my y, my dy dt, derivative of t is just 1. Okay, that looks great. So let's plug everything in to the formula. 2 pi integral, t is from a to b, so from 0 to 2. Y of t is just my y from the parametric equation, so y is equal to t. Square root dx dt is 2t squared plus dy dt is 1 squared dt. So there's t square root 4t squared plus 1 dt. Now to move forward here, I'm going to want to use a substitution. I have this gross thing underneath the square root. I could try trig substitution, but I think that with the t on the outside, it'll be easier just to, let's let u equal 4t squared plus 1. So I get a du of 8t dt. And I just have a t dt up here, so that's 1/8 du is t dt. And so we can plug everything in to get 2 pi. Oh, I need to change these t values. If t is equal to 2, then u is equal to 4 times 4 plus 1 is 17. If t is equal to 0, then I get 0 plus 1 is 1. So from 1 to 17 for the u values, t dt becomes 1/8 du, and square root of 4t squared plus 1, that just becomes square root of u, so u to the 1/2. 2 pi 1 to 17. In fact, I could pull out that 1/8 to make that pi over 4, integral from 1 to 17 u to the 1/2 du, and that will integrate to u to the 3/2 times 2/3 from 1 to 17, and then plug in the top minus the bottom. Let's see, the 2/3 cancels here and here. That's pi over 6. Quantity, I pulled out the 2/3 already, so 17 to the 3/2 minus 1 to the 3/2 is just 1. And that will not simplify any. So there it is, my final answer.